The engine, the vital part of a motor vehicle, comes in various types, including gasoline and diesel-powered types. Presently, four-stroke gasoline engines are widely used. We are now going to learn the basics and the overhauling procedure of the four-stroke gasoline engine through 2 volumes of videotape. This video, Volume 1, will provide you with basic knowledge concerning the construction and function of the gasoline engine. This is a four-stroke gasoline engine. It is composed of a cylinder block, pistons and a crankshaft, a cylinder head, a camshaft, and other parts. An engine is operated by power generated through combustion, the explosion of a mixture of fuel and air filtered through an air cleaner. The explosive power pushes down each piston, causing the crankshaft to rotate. The rotary motion of the crankshaft is transmitted through the clutch and transmission system to rotate the wheels. As the name indicates, the four-stroke gasoline engine operates in continuous cycles of 4 strokes, starting with the air-fuel mixture intake and ending with the exhaust of combustion gas. These are the intake, compression, combustion, and exhaust strokes. For the intake stroke, the exhaust valve is closed and the intake valve is opened. As the piston is lowered, the upper cylinder space increases, making the internal pressure of the cylinder negative. The mixture of fuel and air is then drawn through the intake valve into the cylinder. When the piston completes its downward stroke, the intake valve is closed. The air-fuel mixture drawn into the cylinder is then compressed gradually as the piston is raised. When the piston almost completes its upward stroke, an electric current applied to the spark plug causes it to spark, instantaneously exploding the air-fuel mixture. This explosive power pushes down the piston, causing the crankshaft to rotate. This is the driving force of the vehicle. At the end of the piston's downward stroke, the exhaust valve is opened. As the piston is again raised, the combustion gas is expelled from the cylinder through the exhaust valve. In this way, the crankshaft rotates 2 turns while the piston moves through the intake, compression, combustion, and exhaust strokes. The engine continues running by repeating these 4 strokes of piston operation, thereby driving the vehicle. What parts constitute a 4-stroke engine? Let's look at the construction. The engine parts are divided roughly into 4 groups by function. Parts for the intake and combustion of the air-fuel mixture. The cylinder head and valve mechanism belong to this group. Parts for compressing the air-fuel mixture are the pistons, piston rings, cylinder block, valves, etc. Parts for transmitting engine power are the connecting rods, crankshaft, bearings, and flywheel. Parts for generating sparks are the spark plugs, distributor, etc. These engine parts interact to drive the vehicle smoothly. Now, let's study the major parts of an engine in detail. The cylinder head is in the upper section of the engine. Since the cylinder head is located immediately above the cylinder block, it is always exposed to high temperature, high pressure combustion gas. Therefore, it is made of cast iron or aluminum alloy with high strength and high thermal conductivity. The bottom of the cylinder head is recessed, forming a combustion chamber together with the cylinder and the piston. Engine performance depends largely on the shape of the combustion chamber, as well as installation positions of the valve mechanism and the spark plug. Recent four-stroke gasoline engines use 4 valves for each cylinder, 2 intake valves and 2 exhaust valves. The intake valve is larger in diameter than the exhaust valve to ensure efficient intake. Since these valves are also subjected to high temperature and high pressure, they are made of heat-resistant nickel or special steel such as chromium steel. Each valve is surrounded by related parts such as a valve spring and a valve seat. The valve spring is a coil spring that closes the valve. It forces the valve in close contact with the valve seat, preventing gas leakage. Normally, engines use 1 spring for each valve, although some engines use 2 springs for each valve. When the valve is closed, the valve seat is in close contact with the valve face to secure the air tightness of the combustion chamber. The valve seat is conical with a contact face angle normally of 45 degrees. The contact width is 1.2 to 1.8 millimeters. The cylinder block constitutes the framework of an engine. Together with the pistons, the cylinder block plays the important role of maintaining compression pressure and bearing combustion pressure. The inside of each cylinder is finished to high precision by honing to minimize wear of parts and prevent gas leakage. The cylinder bore is a complete circle. However, the upper part of the cylinder and the piston thrust side tend to suffer from wear due to high temperature and high pressure. Then the clearance between the piston rings and the cylinder increases, resulting in compression loss. The piston moves up and down in the cylinder under pressure generated by the explosion of the air-fuel mixture. This is the construction of a piston. The piston rotates the crankshaft via the piston pin and the connecting rod. The piston is not a complete circle, but is somewhat elliptical in cross-section. The diameter in the direction of the piston pin is slightly smaller to allow for thermal expansion of the piston pin boss. The piston head becomes far hotter and therefore expands more than the skirt. To compensate for the difference in thermal expansion, the piston diameter at the head is made smaller than that at the skirt. The piston rings prevent compression pressure leakage through the clearance between the cylinder and the piston. Normally, each piston has 3 rings. The upper 2 are compression rings, which maintain the air tightness of the combustion chamber and transfer piston heat to the cylinder wall. The lowest ring, the oil ring, scrapes oil off the cylinder wall, leaving the minimum necessary oil film thickness on the wall to prevent excess oil from entering the combustion chamber. Every piston ring has a ring end gap to allow for ring expansion. The end gap is 0.2 to 0.5 millimeters at ordinary temperatures. The connecting rod links each piston to the crankshaft so that the piston's vertical motion is converted to rotary motion. Since the connecting rod is subject to continuous compressive force, tensile force, etc., it must be rigid enough to endure these loads. In assembly, make sure to select a bearing cap suitable to the connecting rod. The crankshaft converts the linear motion of each piston to rotary motion via the connecting rod. The crankshaft is composed of crank pins, which transmit the piston force to the shaft, crank journals, which govern the rotation of the shaft, and balance weights, which ensure well-balanced rotation of the shaft. The crankshaft rotates at high speed under the heavy load applied by the pistons. It must therefore be sufficiently strong and rigid and well-balanced both statically and dynamically. To meet these requirements, the surface of each crank journal and crank pin is hardened to a depth of 2 to 3 millimeters for high wear resistance and toughness. The crankshaft bearings receive the impact load of the explosion applied to the rotary parts of the crankshaft, such as the journals and crank pins, as well as the loads of these parts themselves. An oil film of an appropriate thickness is formed on each bearing surface to prevent seizure of the rotary parts and minimize frictional damage to them. The bearings also ensure airtight contact of the crankshaft with the cylinder block and bearing caps, thereby enhancing heat radiation performance. The gap between the crankshaft and each bearing is called the oil clearance. The oil clearance is normally between 0.02 and 0.06 millimeters. A larger oil clearance causes abnormal noise or a decrease in hydraulic pressure. We have studied the major parts of the engine. An engine can produce high power only when all these parts function normally. Among the many engine parts, the valve mechanism is especially important and complex. Let's take a close look at the valve mechanism. The valve mechanism is designed to operate the intake and exhaust valves, which control the intake of the air-fuel mixture into the cylinder and exhaust the combustion gas out of the cylinder at the proper timing. We will now study the mechanism of opening and closing the valves. In a 4AF engine, the rotary motion of the crankshaft is transmitted through the timing belt to the camshaft. Some engines use a timing chain or timing gear instead of a timing belt. The camshaft timing pulley has twice as many teeth as the crankshaft timing pulley, so that the camshaft rotates once while the crankshaft rotates twice. As the camshaft rotates, the cams rotate, opening or closing the valves. The valve mechanism can be divided into various types according to the number of camshafts and the camshaft position relative to the valves. The DOHC, double overhead camshaft valve mechanism, has two camshafts which operate the valves directly. With a complicated construction, this type of valve mechanism ensures accurate operation of each valve, resulting in improved intake and exhaust efficiencies, high engine output, and good fuel economy. The OHC overhead camshaft valve mechanism uses one camshaft to operate the valves and therefore requires rocker arms. The OHV overhead valve mechanism has a camshaft in the lower part of the cylinder block and therefore requires push rods and rocker arms. Despite its simple construction, this type of valve mechanism is hardly used today. The intake valve only has to be kept open while the piston is in the intake stroke. And the exhaust valve has to be kept closed while the piston is in the exhaust stroke. However, valve timing must take into account the fact that the inertias of both intake and exhaust increase as the engine speed increases. Specifically, the intake valve starts to open before the piston begins its intake stroke and closes after the stroke. Similarly, the exhaust valve starts to open before the piston begins its exhaust stroke and closes after the stroke. Such valve operation timing ensures efficient intake and exhaust. A chart showing valve operation timing in terms of crankshaft angle is called a valve timing diagram. As this diagram shows, each valve is opened or closed earlier with respect to the piston position in each stroke, thereby improving the intake and exhaust efficiencies, as well as enabling each valve to be fully open at the optimum time. There is a period of time during which both intake and exhaust valves are open. This period is called valve overlap. To enable each valve to open or close smoothly, appropriate clearance must be provided around the valve. This is called valve clearance. Excessive valve clearance causes abnormal noise and improper valve operation timing. Insufficient valve clearance causes incomplete valve closure, resulting in insufficient compression. The valve clearance must be adjusted to an appropriate value. The valve clearance in a cold state is different from that in a hot state, as the valve clearance is affected by temperature. Next, let's study the engine lubrication system. An engine is assembled from numerous metal parts, many of which rotate at high speed under high temperature conditions. If these parts are not lubricated, they generate heat due to friction, causing wear or seizure. The lubrication system is indispensable for smooth engine operation. The lubrication system is composed mainly of an oil pan to store engine oil, an oil pump to pressure feed the oil to various parts of the engine, an oil filter to remove impurities from the oil, and an oil cooler. The lubrication system supplies engine oil to each part of the engine so as to force an oil film on part surfaces, thereby minimizing friction and wear. Parts thus lubricated rotate or slide smoothly, enabling optimal engine performance. Four-stroke engines normally use a pressure-type lubrication system. In this type of system, engine oil stored in the oil pan is first filtered through the oil strainer and then sent to the oil pump. The oil pumped up by the oil pump is further filtered through the oil filter and sent through the main oil gallery of the cylinder block to each crank journal and crank pin of the crankshaft. The oil is jetted out to lubricate the pistons and cylinders. Simultaneously, oil is supplied to the valve mechanism. The oil is then returned to the oil pan. Now, let's look at each major part of the lubricating system. A trochoid pump is usually used to pump oil. The procedure of oil pressure feed is as follows. The drive and driven rotors rotate while interlocked. Since the drive rotor shaft is slightly eccentric, a space is produced between the two rotors as they rotate. The oil is pressure supplied through this space. The oil pump has a relief valve which adjusts the maximum oil pressure. When the oil pressure reaches a specified value between 3 and 6 kilograms per square centimeter, the relief valve opens to adjust maximum oil pressure. The oil filter removes fine impurities such as powder and carbon from the engine oil. The filter comprises a check valve, filter element, and relief valve. Oil from the oil pump pushes open the check valve, entering the outer circumference of the filter element. As the oil passes through the element to the filter's center, impurities are filtered from the oil, which is then sent to each part of the engine. If the filter element is closed, the oil pressure at the filter outer circumference becomes higher than that at the center. When the pressure difference becomes about 1 kilogram per square centimeter, the relief valve opens to create a bypass, allowing the oil to flow directly to the engine without passing through the filter element, thereby preventing insufficient lubrication. Engine oil deteriorates faster at higher temperatures. The oil temperature should therefore be maintained below about 125 degrees Celsius. Since the oil tends to become hot, the engine is equipped with an oil cooler like this to lower the oil temperature. Even if there is no oil leakage, the amount of oil will gradually decrease as the vehicle is used, because, among other reasons, oil is burned in the combustion chamber. Oil is also consumed at 3 other points. Between the cylinder and piston, between the valve guide bushing and valve stem, and in the crankcase emission control system. The cooling system is also essential to the engine. Let's take a look at it. To operate an engine efficiently, the engine must be maintained at an appropriate temperature. Excessive high temperature will result in abnormal expansion or seizure of parts. Too low a temperature, on the other hand, will cause increased fuel consumption and accelerate part wear. To maintain an appropriate engine temperature, it is not sufficient to simply prevent the engine temperature from rising. It is also necessary to raise the temperature quickly to an appropriate value when it is low. In general, a water cooling system is adopted for the cooling systems of vehicle engines. A water cooling system is mainly composed of a water pump, which circulates water as coolant through each engine part and the heater system. A thermostat, which controls coolant temperature. A radiator, which radiates coolant heat to the atmosphere. And a cooling fan, which enhances the radiation performance of the radiator. In this cooling system, coolant circulated through the water jacket absorbs heat generated by the engine, thereby lowering the engine temperature. After the absorbed heat is radiated to the atmosphere by the radiator, the coolant is returned to the water jacket for circulation to cool the engine. There are two coolant flow circuits interswitched by the thermostat. When the coolant temperature is low, the thermostat closes, shutting off coolant flow to the radiator so as to warm the engine quickly. The coolant from the water pump then flows through the cylinder block and cylinder head, returning to the water pump via the bypass. When the coolant temperature becomes high, the thermostat opens, allowing the coolant to flow to the radiator, thus maintaining an appropriate engine temperature. Now, let's look at the main parts of the cooling system. There are two types of cooling systems in terms of a coolant bypass circuit: the inline bypass type, in which the bypass is open at all times, and the bottom bypass type. Most engines use the bottom bypass type. In the bottom bypass type, the thermostat is installed on the coolant inlet side and has a bypass valve. When the thermostat opens, the valve closes the bypass. Compared with the inline bypass type, the bottom bypass type has greater cooling efficiency and less fluctuation in coolant temperature, and therefore achieves more stable engine temperature. The thermostat functions to control coolant temperature. As described earlier, the thermostat opens or closes depending on coolant temperature. Normally, the thermostat starts to open at a coolant temperature between 80 and 84 degrees Celsius and fully opens at 95 degrees Celsius. If the thermostat is closed when coolant is injected into the cooling system after drainage, engine side air will remain in the cooling system, hampering coolant injection. To avoid this, the thermostat has a jiggle valve at the flange. Engine side air is drained through this valve to facilitate coolant injection. The water pump forces coolant through the cooling system. The rotary motion of the crankshaft is transmitted through the timing belt and V-belt to drive the pump rotor. The pumping function of the rotor circulates coolant in the cooling system. The gap between the rotor and water pump body is mechanically sealed to prevent coolant leakage. If coolant leaks through the mechanical seal, it can enter the bearing section. To prevent this, the water pump is provided with water drain holes. Coolant leakage can be checked through these holes. To enable the radiator to radiate heat, large quantities of air must be led into the radiator to cool it. While the vehicle is running, the radiator is cooled by natural ventilation. While the vehicle is stopped, however, the cooling fan must be used to force air into the radiator. There are two types of cooling fan, the temperature-controlled fluid coupling type and the motor-driven type. The temperature-controlled fluid coupling fan changes its speed between two levels according to the air temperature in the radiator. When the air temperature is low, fan speed is kept at low level to quicken engine warm-up and reduce fan noise. When the air temperature becomes high, the fan speed changes to a high level to increase cooling performance. The motor-driven fan is activated only when the coolant temperature is high. Most front-engine, front-wheel drive vehicles use this type of fan. Since the fan speed does not change with the engine speed, this fan provides high cooling performance when the vehicle is driven at low speed. We have studied the basics of a four-stroke gasoline engine. The engine is composed of many intricately interrelated parts. The engine will not work satisfactorily if even one of these parts is missing. You should thoroughly understand the construction of gasoline engines through this video, Volume 1 and Volume 2 on the overhauling procedure, as well as through Toyota's technical training manual, so that you can provide proper technical services to satisfy our customers.